Hello, ladies and gentlemen. Uh, our today's compensatory lecture is intended to prove some facts which follow from the fundamental theorem of arithmetics we proved last time. You know, the fundamental theorem of arithmetics says that every natural number greater than 1 and in fact greater than 0 can be uniquely represented in the following form as a product of some distinct prime numbers to natural powers, that is P1, P2, Pt, and so on are pairwise distinct primes, where I are just natural numbers, maybe including 0. For example, for 1, we have just 1 factorization. Recall that such representations are known as prime factorizations. For 1, we have just 1 factorization where every prime is present in the degree 0. In fact, it doesn't matter which prime we put into this product given their degrees are all 0. And what does it mean that this representation, this factorization is unique? You know, say 15 may be expressed like 3 to the power 1 multiplied by 7 to the power 0 multiplied by 5 to the power 1. And another representation is 11 to the power 0, 2 to the power 0, 5 to the power 1, 3 to the power 1. That means that every prime has must have identical degrees in any two prime factorizations of a number. That is, 11 has degree 0, and here it also has degree 0. If it is not explicit, that means that it has degree 0. You know, every number to the power 0 is 1, and we are free to assume that 11 is present here, but in degree 0. So far, so good. And now let us extract a bunch of corollaries from this fundamental theorem of arithmetics. It is indeed fundamental, for we have a lot of important corollaries. The first one is that there are infinitely many prime numbers. There exist infinitely many primes. What does it mean, infinitely many? That means that, of course, we had no rigorous definition for an infinite set, but intuitively it is enough to prove that it is not true that we have just n primes for whatever natural number n. So if it is possible to derive a contradiction from an assumption that we have just so many, just n primes, that means that there are infinitely many of them. Okay, so for the sake of contradiction, assume that P1, P2, and so on, Pn are all primes, are all primes in existence. So there are no other prime. There is no other prime. How many primes do we have? We know that 2 is prime, hence at least one prime exists, so this number n is at least 1. We have at least one prime. Okay, and now let us consider some specially crafted number, capital N. This capital N will be the product of all our alleged primes plus 1. So what can we say about it? Clearly, this number is at least 3, because in this product we have 1, so it is at least 3, or anyway it is greater than 1. Okay. According to the fundamental theorem of arithmetics, this number must have some prime factorization. Okay, what is it? It is greater than 1, it is either prime or composite. Can it be prime? If n is prime, we have that n is greater than any of these primes. It is greater than any of them. So we have a contradiction. It is not possible for this number to be prime because it is distinct from any of our primes. So it is not prime. We know that every number is either prime or composite. So then, n is composite because it is greater than 1, and every number greater than 1 is either prime or composite. Okay, but if it is composite, then there is a non-trivial divisor of this number. And in general, by the fundamental theorem of arithmetics, there is a prime divisor of this number. In fact, considering this case when n was prime is not necessary. Anyway, by the fundamental theorem of arithmetics, there is a prime divisor of this number. It is greater than 1. So it is a product of some primes to some degrees, a1, a2, and it is not possible to have all these degrees being equal to 0. So there exists a prime which divides our number n. So by the fundamental theorem of arithmetics, some pj divides n. There is a prime factorization, and not all the degrees equal 0 because our number is greater than 1. It's divisible by n. And what do we have? Pj divides n, that is this sum, where pj is, of course, present. And pj divides this product. What does it mean? Then clearly, pj must divide 1, which is not possible. A prime number cannot divide 1. That's all. In fact, considering this case, when n itself was prime is not necessary. Okay, let us repeat the proof. Take capital N of this form, conclude that it is greater than 1 because we have at least one prime and this product is at least 2. So every number is divisible by every number greater than 1 is divisible by at least one prime. So there exists such j that pj divides n. So pj divides this sum, and pj the contradiction from the assumption that we have just these primes, just n of them. Hence, there are infinitely many primes. Another important corollary is the so-called divisibility criterion. In order to state this criterion, let us firstly extend the notion of prime factorization to negative numbers. Assume that we have, say, minus 15. We can call its prime factorization the following product: minus 1 multiplied by 3 to the power 1 multiplied by 5 to the power 1. So what is the prime factorization of a negative number? If n is negative, then its prime factorization is just minus 1 multiplied by a factorization of its absolute value. So we can say that every negative number also has a prime factorization, which is obtained by multiplying a factorization of its absolute value, which is unique, as we know, by minus 1. With this in view, we can state the following important divisibility criterion. Divisibility criterion. For any integers a and b, let us exclude 0 from our consideration. Let a has some factorization p1 to the power alpha 1 and so on, pt to the power alpha t, which can be also multiplied by some epsilon, which represents its sign. And the same for b. Where epsilon and delta are either 1 or minus 1, these signs. So let us consider these two factorizations. They are uniquely determined in terms of assigning degrees to the primes. So we can easily identify any given integers with their factorizations. Okay, then I want to state the following. A divides b if and only if every prime has not greater degree in A than it has in B. So for each I, alpha I is less or equal than beta I. What does it mean? That means that in order to compare two integers in terms of divisibility, it suffices to compare the exponents of each prime, показатели степени, the exponents of each prime in their factorizations. And those factorizations are uniquely determined. That is, given an integer, you know the degree of each prime uniquely. You know it for sure. Okay, let us prove this fact. From the left to the right, assume that A divides B. Then, by definition, there exists some integer k such that B equals A multiplied by k. What does it mean? First of all, we know that k is not 0 because B is not 0. As B was not 0, then k is not 0 as well. So we may factorize it. Let us factorize k. Let us construct its prime factorization. It is something. It is some epsilon, eta. It is some eta which stands for the sign, multiplied by p1 to the power gamma 1, and so on. We have factorized it. And what do we have? Let us consider this equation. So delta multiplied by this factorization of B but the right-hand side clearly equals p1 to the power alpha 1 plus gamma 1 and so on. So far, so good. And now we have one number with two prime factorizations. So what is, one can ask, what is the degree of, say, P1 in the factorization of this number? On the one hand, this degree is beta 1. But on the other hand, according to this alternative factorization, it is alpha 1 plus gamma 1. But by the fundamental theorem of arithmetics, these degrees must be uniquely determined. That is, beta 1 must equal alpha 1 plus gamma 1, and the same for all I. Beta I must equal alpha I plus gamma I, because there is no other way to determine the degree of pi than to take it as bi. That means that beta I equals alpha I plus gamma I. But we know that gamma I is a natural number by the definition of a prime factorization. Hence, beta must be greater or equal than alpha. Okay, and for the other direction now, assume that indeed for each I, beta I is less or greater or equal than alpha I. What should we do? We want to construct this k, and it is not hard to do. It is not hard to do. Let us consider the following number k. We take delta divided by epsilon. You know, delta and epsilon are either 1 or minus 1. You can freely divide or multiply them by each other. Okay. And here we take p1 to the power beta 1 minus alpha 1 and so on. And our inequality here guarantees that every such number is natural. It is greater or equal than 0. Hence, this number is an integer. We have defined it by its factorization. Why not? And our last step is just to compute a multiplied by k. What is it? A is this number. And k is just this one. And now we know that when multiplying these two, we will obtain p1 to the power beta 1. And the same for other primes, which is b. So indeed, b equals a multiplied by something. Hence, b is divisible by a. A divides b. So what does it mean? That means that, let me reiterate. Here we see that comparing two numbers by divisibility relation, where the one divides the other one, is equivalent to comparing the exponents of all the primes and their factorizations. It is a very important fact of many implications. So far, so good. And now we are ready to introduce the greatest common divisor. What is the greatest common divisor of two or more numbers? It is not hard to see that this number must likely be a common divisor of the two. But in which sense is it the greatest one? In the high school teaching, they usually say that the greatest common divisor of two integers is such the common divisor which is the greatest in terms of our natural ordering of numbers, where say 3 is greater than 2. But putting things this way, one have no greatest common divisor for say 2 zeros, because every number is a common divisor of 2 zeros. But among naturals and integers, we have no greatest number. But this way is quite unnatural. It is way better to define the greatest common divisor the following way. Let a and b be two integers, including 0, of course, why not? We say that d, which is natural by definition. Please notice that the greatest common divisor must be natural. It is by definition. We say that d is a. Okay, a greatest common divisor, for there is no reason so far to presume that it is unique and so on. Is the greatest common divisor of A and B is the greatest common divisor of A and B In symbols, we put it the following way. D equals GCD of A and B, but please be careful here. For this symbol alone is not enough to prove uniqueness. So in principle, it may be so that GCD of A and B equals D1 and GCD of A and B equals D2, while D1 differs from D2 in principle. It is still possible. We should exclude this possibility, but nevertheless. So D is called the greatest common divisor of A and B if and only if the following two properties hold. First of all, D is a common divisor of A and B, divides both the numbers, and it is the greatest one in the following sense. Let me put it in words first. D is divisible by any common divisor of A and B. So in this sense, it is the greatest one. It is divisible by any common divisor. And now let us use quantifiers. For every D prime, in fact, you can restrict it to naturals because x is divisible by y if and only if x is divisible by minus y. The sign matters little here. For every natural number d prime, if d prime is a common divisor of A and B, then D prime divides D. So it is the greatest one in the following sense. It is less or equal than D in terms of divisibility, not in terms of less or equal in general. But this begs the question. Is it true that for every two integers we have a greatest common divisor? And another question. Is it true that this greatest common divisor, given it exists, is unique? In fact, both questions have positive answers. Okay. For every 2A and B, there exists a unique number D such that D is the greatest common divisor of A and B, and this fact justifies the symbol. For now, D, if something equals GCD of A and B, there is no other possible value for GCD of A and B. It is unique. If D1 equals GCD of A and B and D2 equals GCD of A and B, then D1 must equal D2. Okay, let us prove it. First of all, we shall prove uniqueness and then existence. So for uniqueness, assume that D1 and D2 are greatest common divisors of A and B, both. Everyone is the greatest common divisor. What do we have then? You know, D1 is a common divisor. But D2 was the greatest common divisor. So let us put it in words. So here we have that D1 is common. That is common divisor. D1 is common. But D2 is greatest. It is the greatest one. That means that every common divisor, including D1, divides D2. So we have that D1 divides D2. And similarly, D2 is a common divisor. But D1 is the greatest common divisor. Hence, D2 must divide D1. So here we have these two divisibility statements, from which it follows that our numbers may differ in their signs only, but they are both naturals. So we know now that they are equal. So this uniqueness is inferred from this definition. It is quite clear. And existence is slightly harder. The existence claim is slightly harder. First of all, let us consider some cases. The first case is when A equals 0. If A equals 0, we know that B divides A and B divides B. So our first idea is to take B is the greatest common divisor. Of course, no divisor of B can be greater than B itself. But here we have a minor problem with the sign of B. So let us take the absolute value of B. Clearly, the absolute value of B is everything divides 0. Likewise, the absolute value of B divides B. And I want to prove that it is indeed the greatest one. Okay, if everything is checked directly against the definition, assume that some D prime divides 0 and divides B. If D prime divides our A, that is 0, and D prime divides B, then it is quite clear that D prime must divide the absolute value of B, which is our alleged greatest common divisor. Hence, indeed, by definition, our D equals the greatest common divisor of 0 and B. And the second symmetric case is when B equals 0. Then, of course, similarly, the greatest common divisor of A and 0 equals the absolute value of A. And the third case, the most interesting one, is when neither A nor B is 0. In this case, we can factorize according to the fundamental theorem of arithmetic. So, when factorizing, we may obtain A being equal to epsilon, which is its sign plus or minus 1, multiplied by this product. What's next? Now we want to construct our greatest common divisor. It is quite clear that this common divisor is not 0, so we can construct it using its factorization. And we need a number which, according to the divisibility criterion, we need a number where every prime's degree is less or equal than both alpha and beta. And it is easier to take such a number. So let D equal P1 to the power minimum of alpha 1 and beta 1. So this way, we can construct a computational recipe to obtain the greatest common divisor. If you know factorizations, it is easy to construct the greatest common divisor. Okay. So far, we have constructed this number, and now we need to check two things. D is indeed the common divisor, so it is common, and it is greatest. Why is it common? You know, minimum of alpha I and beta I is, of course, less or equal than alpha I. Hence, by the divisibility criterion we proved earlier, by the divisibility criterion, it is enough to say that our D divides A, because every prime has lesser or equal degree there than it has in A. So D divides A by our theorem 2, by the divisibility criterion. And likewise, of course, this minimal value is less or equal than beta I for every I, hence D divides B. As I have already said, in order to prove that one number divides another one, it is enough to compare the exponentials of every prime and their factorizations. And by the fundamental theorem of arithmetics, these exponentials are uniquely determined. So D is indeed the common divisor of A and B, and it is the greatest one. Okay, let us do so. Assume that we have some common divisor, D prime. D prime divides A and B. As neither A nor B were zero, that means that D prime is not zero as well. You know, a non-zero, zero cannot divide a non-zero number. Then D prime is not zero, so we can factorize it. It is a natural number, so its factorization has this form, p1 to the power gamma 1, and so on. But what does it mean? By the same divisibility criterion, or theorem 2, we have that for each I, gamma I is less or equal than alpha I, then the degree pi has in the factorization of A. And likewise, of course, gamma I is less or equal than beta I. Taking these two together, have that gamma I is less or equal than the minimal of these two values. So that means that D prime divides our D. Okay, that's all. We have constructed a number which is the greatest common divisor according to our definition. Likewise, we have a computational way to obtain such a number given a factorization is known. In fact, this assumption is very important because in general it is hard to obtain a factorization, but for small numbers it is not that hard, and now we can try computing the greatest common divisor. Say, what is the greatest common divisor of minus 91 and say 28? What is the greatest common divisor? Neither number is zero, so it is not zero, but we need to factorize. Minus 91 is minus 1 multiplied by what? Multiplied by 7 to the power 1 by 13. Indeed, it is 70 plus 21. And on the other hand, 28 is 7 to the power 1 multiplied by 2 to the power 2. So what is the greatest common divisor? First of all, it is positive, so no minus 1 here. 7 to the power minimum of 1 and 1. 13 to the power minimum of 1 and 0. Here we have 13 to the power 0 in degree 0 and 2 to the power 0, minimum of 0 and 2, which is just 7. So 7 is the greatest common divisor. Okay. And now let us obtain some properties of this greatest common divisor, which will prove important later. Lemma 4. For every 3 integers a, b, and q, the greatest common divisor of a and b equals the greatest common divisor of a plus b multiplied by q and b. What does it mean? So intuitively, that means that when computing the greatest common divisor, you can say move a few copies of b to the first argument. Of course, it is not hard to prove that the same way you can move some copies of a to the second argument, and then the greatest common divisor won't change. In general, the greatest common divisor is symmetric. The GCD of a and b always equals the GCD of b and a, but we shall prove it in our seminar class. But so far, let us check this fact. It is very easy to prove it applying the definition. Okay. You know, every two numbers has some greatest common divisor. Let D be the greatest common divisor of this number, and D prime be the greatest common divisor of this number. Our next goal is to prove that D divides D prime and D prime divides D, whence they are equal. Okay, what do we have? By definition, D divides A and D divides B. But that means that clearly D divides A plus B Q. Why not? If it divides B, then it must divide B multiplied by Q. So it divides the sum of these two numbers. Aha! And still, of course, it divides B. So our D is a common divisor of these two numbers, of which D prime was the greatest common divisor. So as D prime was the greatest, then D must divide D prime. And likewise here, D prime by definition divides this sum, and it divides B. So D prime divides BQ, and also minus BQ, of course. Then D prime divides A plus BQ minus BQ. So D prime divides A, and it still divides B. So D prime is a common divisor of A and B, of which D was the greatest common divisor. Hence, D prime must divide D. We have two naturals where everyone divides the other one. Hence, these two naturals are equal. That's all. Nothing else than applying the definition. Okay. When computing the greatest common divisor, you can freely move a few copies of the first argument to the second one and vice versa. As a corollary, that means a very important fact. For every two numbers a and b, the greatest common divisor a and b equals the greatest common divisor of b and the remainder after dividing a and b. Of course, this makes sense for non-zero b only. So the greatest common divisor of a and b always equals the greatest common divisor of b and the remainder. Why is it so? By the integer division theorem, we have that for some q, a equals b multiplied by q. This q was the partial quotient plus the remainder. That is our a. The remainder of dividing a by b is just a minus bq. So this remainder is the greatest. The greatest common divisor of these two numbers is b, is the greatest common divisor of b and a minus b, which equals the greatest common divisor of b and a, or a and b. They're equal. According to our previous theorem. So here we have moved a few copies of b here. This will not change our greatest common divisor. That's all. It is a very special case when the greatest common divisor of two numbers equals 1. In this case, they say that our numbers are coprime. Let us give the definition. A and B are called coprime, like prime, but with this prefix co. That is prime to each other, with respect to each other. A and B are coprime if and only if the greatest common divisor equals 1. For example, we say that 15, which is 3 multiplied by 5, and say 28, which is 7 multiplied by 2 squared, are coprime. Neither of these two numbers is prime, but they have no common prime divisor. Their only common divisor is a natural number. Their only common natural divisor is 1. So they are coprime. And in general, we have another characterization of this coprimality. Lemma 6. We say that the following statements are equivalent. the following statements are equivalent. A and B are coprime, that is, the greatest common divisor is 1. The only common natural divisor of these two numbers is 1. They have no common prime divisor for every n. If n divides A and n divides B, then n is not prime. N is not prime, and given A and B are non-zero, that means that for each I, the minimum of their prime degrees is 0. That is for every prime. Let us factorize them. If A was, say, P1 to the power alpha 1 and so on, and B was P1 to the power beta 1, Pt to the power beta t, and so on, then the minimal value of these exponentials is always 0. How can one prove it? In general, it is obvious. In general, it is quite obvious. Okay, if the greatest common divisor was 1, then every common natural divisor must divide 1. But if it divides 1, it equals 1. So this one is clear. Next, if every common divisor is 1, then of course it is not possible to have a common prime divisor, because no prime number is 1. Okay, now assume that they have some factorizations. Now it is quite clear, the greatest common divisor is P to the power P1 to the power minimum of alpha 1, beta 1, and so on. And on the other hand, it is 1. So it is P1 to the power 0 and so on. Then, by the fundamental theorem of arithmetics, for we have just one prime factorization, that means that the minimum here is always 0. So from the first one, it follows the fourth one. And from the fourth one, okay, from the first one it follows the fourth one. From the fourth one, it clearly follows the third one. Why? Because that means that no prime has a positive degree in these two numbers factorization. So there is no prime which divides both of them. And now the only remaining thing to prove is to obtain 1 from, say, 3. Okay, if we have no common prime which would divide these numbers, then the greatest common divisor is not divisible by any prime. It is not divisible by any prime. So the only number which is not divisible by a prime, being natural, is just 1. If for every two numbers we have a greatest common divisor, but no prime is a common divisor, hence no prime divides the greatest common divisor, so this greatest common divisor is just 1. But anyway, this statement is very, very elementary, to that degree that it may be called obvious. But nevertheless, let us notice this fact. Lemma 7. It is interesting that we may transform every two non-zero numbers into coprime ones in some unified way. So for every two a and b, which are not zero, these numbers a divided by the greatest common divisor of a and b divided by the greatest common divisor of a and b, these two numbers are coprime. So we can divide every two numbers by their common divisor, greatest common divisor, and obtain a pair of coprime numbers. Why is it so? It is quite obvious to obtain. As usual, let a be epsilon multiplied by this one. What is a prime? What is a prime? A prime is just a divided by the greatest common divisor. So here we have alpha 1 minus the exponent in the greatest common divisor. That is this thing. And the same we have for b prime. And now I want to prove that these two are coprime. In order to prove that they are coprime, it is enough to prove that the minimum of these two exponents, namely, the minimum of these two exponents is always 0. It is not possible that both of them are greater than 0. Okay, let us compute this minimum. What is the minimum of alpha I minus the minimum of these two, and beta I minus the same minimum? It can be checked by cases. First of all, what if alpha I is less or equal than beta I? We have here minimum of alpha I minus alpha I and beta I minus alpha I. But here we have 0. This one is 0. Hence, this entire minimum is just 0. Similarly, if beta I is less or equal than alpha I, here we have alpha I minus beta I, and here we have beta I minus beta I, which is 0. Hence, this whole minimum is 0. So in any case, it is 0. Of these two exponents, one is surely 0. So it is not possible that these two numbers share a prime divisor. Hence, they are coprime. Another important lemma shows that it is possible to somehow cancel a number coprime to something from a divisibility statement. Okay, this lemma is quite important. Please notice that. Assume that A divides the product of B and C, while A and B are coprime. So assume that A divides a product of two numbers, of which one is coprime with A. So that means that A must divide the remaining number. A must divide the remaining number. This fact is very important and frequently used. So if A divides something, you can exclude, you can cancel from this product everything which is coprime with A. Okay, let us prove this important statement. The first case is when C equals 0 or A equals plus or minus 1. You know 0 is divisible by everything, while 1 and minus 1 divide everything. So everything is okay here. It is trivial. And for the second case, we see that neither C equals 0 nor A equals plus or minus 1. Now I want to prove that B is non-zero as well. B is non-zero as well. Why is it important? Because I want to factorize B. I want to factorize all the numbers here. But I cannot factorize 0, okay, and I cannot construct a prime factorization of 0. Hence, I want to make sure that my numbers are non-zero. For the sake of contradiction, assume that B is 0. Okay. We know that the greatest common divisor of A and B is then it is we have proved that if one number is 0, then the greatest common divisor equals the other number. But we know that it is 1, for they are coprime. But then A is plus or minus 1, which is not the case. So B is not 0. C is not 0, B is not 0, so we may freely factorize these numbers. But what about A? May A be 0? No, because then B multiplied by C is neither 0, and as A divides their product, that means that A is not 0. I said. Okay, B is not 0, C is not 0, A is not 0. So now we may factorize them freely. Let A be epsilon multiplied by P1 to the power L for 1 and so on. What do we have then? We know that A divides BC. So by our divisibility criterion, that means that for every I, the degree of pi in A, which is alpha I, is less or equal than the degree of pi in this product, B multiplied by C. And that degree is just beta I plus gamma I. On the other hand, we know that the greatest common divisor of A and B is just one, their coprime. If they are coprime and they are non-zero, that means that the minimum of these degrees, alpha I and bi, is always 0. Or equivalently, either alpha I is 0 or beta I is 0. So for every I, we have two cases. The first case is when alpha I is less or equal than beta I plus gamma I, and AI is 0. This is the first case. And the second case results from beta I being equal 0. Okay. And for the first case, what do we need, by the way? We have to prove that A divides C. That is, alpha I is less or equal than gamma I. Of course, when alpha I is 0, it is guaranteedly less or equal than gamma I for every I. And here, you know, we see that alpha I is less or equal than beta I, that is 0 plus gamma I. Alpha I is less or equal than gamma I for every I. In both these cases, we can obtain that A divides C. A divides C. So, you know, for for distinct i's, either one case takes place or the other one. But in any case, we have alpha I being less or equal than gamma I. So for each I, alpha I is less or equal than gamma I. That means that A divides C. And this was the thing required to be proved. That's all. So that means that we can somehow cancel out a coprime factor from a divisibility statement. And that means that you can sometimes cancel a number out of a congruence. Another important corollary. If A multiplied by X is congruent to A multiplied by Y modulo M, and this factor M is coprime to the modulus, then X is congruent to Y modulo M. So you may cancel it out. You may cancel it out somehow, given, of course, it is coprime with M. For example, say 3x is congruent to 3y modulo 5. That means that x must be congruent to y modulo 5, because 3 and 5 are coprime. But be it 15 here, it wouldn't be the case in J. Let us show that this coprimality assumption is important. Assume that, for example, we have not 5 here, but 15, which is not coprime to 3. Then 3 multiplied by 5 is, of course, congruent to 3 multiplied by 15, modulo 15, because both of these are congruent to 0. Both these numbers are divisible by 15. But, of course, 5 is not congruent to 15, that is to 0 modulo 15. It is very important to have this factor to be coprime to the modulus. How can one prove it? Prove it's really elementary, as ax is congruent to ay modulo m, then m, that means that that m divides the difference of our numbers. It divides ax minus ay. That is m divides a multiplied by x minus y. But given m and a are coprime, we have that then m divides x minus y. So x and y are congruent modulo m. Okay, let us repeat. It is possible to cancel, to divide both sides of a congruence by any number coprime to the modulus. Another important thing as concerning coprime numbers is that one can combine these numbers, that is, multiply by them by something and add together the results in order to obtain 1. So theorem 10. This is known as Bezout's identity. Bezout was a French mathematician of the 17th or the 18th, early 18th, probably the 17th century. So Bezout's identity. For every two integers, if these integers are coprime, then there exist some other integers s and t, or let us denote them u and v. There exist some integers u and v such that au plus bv equal 1. So it is possible to obtain 1 by adding together some copies of A and some copies of B, given they are coprime. For example, if we have, say, 5 and 3, how can one obtain 1? It is not hard. One should take 2 copies of 5 and subtract 3 copies of 3. This will be 1. You can always obtain 1 given these two numbers are coprime. But if they are not coprime, in general it is not possible. Why is it so? Say 5 and 15. 5u plus 15v is divisible by 5 for whatever u and v. So this number may not equal 1. But for coprime numbers, it is always possible to obtain 1. And in fact, every other number, so 1 is not that specific. The main idea here is that if you have obtained 1, you can easily obtain whatever number, say 17, just by multiplying this u and v by that number. And this fact proves important for solving equations, for integer variables. Okay. Now let us prove Bezout's identity. This will require some induction, as usual, in the form of the least number principle. Let us consider some property phi. Phi is phi of d would mean that there exists some s and t, some integers, of course. Every number is integer by default in our treatment. There exists s, there exists t, such that d equals as plus bt. So our d is a linear combination of a and b. It is of this form. But besides that, I would require that d is greater than 0. So let us consider the following property: to be a positive linear combination of a and b. This property can be satisfied, so it is not an empty property. Why is it so? Okay, let us prove. As the GCD of A and B is 1, it is not 0. That means that either A or B, at least one of them is not 0. At least one of these numbers is not 0. Without loss of generality, let A be non-zero. If A is non-zero, we can take the following. We can take this number D. A multiplied by the sine of A plus B, whatever it be, multiplied by 0. So it equals the absolute value of A, which is positive. Hence, for our D, this property phi holds. Okay, there are such numbers. It is possible to construct a positive linear combination of A and B. But now our next step is to take the least such number. By the least number principle, there exists the least. There exists the least number D 0 such that D0 satisfies 5. So no less a number satisfies for every natural, which is less than D0, our phi doesn't hold. So it is the least number with this property. Okay, as D0 satisfies our property, there exists T such that D0 equals AS plus BT. This is just by definition of phi. What should I do next? I will divide A and B by this D0. Let's divide A by D0. So we have divided it somehow. So A equals D0 multiplied by Q plus R. And of course, this R is greater or equal than 0, but less than D prime. This is the trick. You know, what is R? According to this equation, R equals A multiplied by 1 minus D prime, D0 multiplied by Q. That is A multiplied by 1 minus A S plus BT multiplied by Q. That means that our R is a linear combination of A and B. It is A multiplied by 1 minus SQ plus B multiplied by minus TQ. So it is a linear combination of A and B. But is it positive? You know, R is less than D0. D0 was the least linear combination of A and B. It was the least linear combination of A and B, which was positive. Hence, R doesn't satisfy phi. R does not satisfy phi, so it is by the choice of D0. For D0 was the least number with this property. R cannot least natural with this property. R is natural, but it cannot satisfy phi. But on the other hand, R is a linear combination of A and B. It is a linear combination, but it doesn't satisfy phi. How could it be possible? That means that R is not greater than 0. So the only possibility is that R equals 0. So A is just D0 multiplied by Q. So D0 divides A. And we can repeat the same argument, but for B. Similarly, we can obtain that D0 divides B. D0 divides A. D0 divides B. Hence, it is the common divisor. D0 must divide the greatest common divisor of A and B, which was 1. Hence, D0 was 1. And on the other hand, we have just obtained S and T such that D0 equals AS plus BT. So there exists S and T such that 1, our D0 equals AS plus BT, which was exactly what was required to be proved. We have found U and V, or S and T if you like, with this property. Please notice that this proof was not too good, because there is no explicit way to find this S and T. We have taken some minimal linear combination, but which one is minimal? How can one practically obtain this S and T? Later, we shall see how it is possible. It is not that hard. And the very last point of our today's lecture is a slight extension of this result. Excuse me. Okay, so far we proved Bezout's identity that given A and B are coprime, it is possible to obtain one as their linear combination. And generally, it is possible to obtain the greatest common divisor of any two numbers this way. Corollary 11. For every two numbers A and B, there exists U and there exists V such that AU plus BV equals their greatest common divisor. In order to obtain that, let us recall to our mind that you can easily make every two numbers coprime to each other by dividing them by their greatest common divisor. So for whatever A and B, of course, we have the case of 0 if the greatest common divisor is 0 when there are two zeros. So formally we have some cases. The first case is when A and B are both 0. So the greatest common divisor is 0. what should we do? It is very easy. 0 multiplied by 2021 plus 0 multiplied by 2022 equals 0. So everything is trivial. The first case is when I, the number, is not 0. Then the greatest common divisor is not 0, so it is possible to divide by this greatest common divisor. Then a prime, which is a divided by the greatest common divisor of a and b, formally we can apply our theorem when both of them are not 0, but it doesn't make any change. Okay, let us be slightly more precise, slightly more careful here. So the first case is when I, the number, equals 0. So here the greatest common divisor of 0 and b equals the absolute value of b, and on the other hand, the absolute value of b equals 0 multiplied by whatever number, which is our a, by b, multiplied by b by its sign. So that's all. Here it is similar. And the second case when neither number is 0. Then we may take a prime and b prime. These two numbers are coprime to each other. We know that. It is by our lemma 7. By lemma 7, so by Bezout's identity, by theorem 10, there exists S prime and T prime such that 1 equals A prime S prime plus B prime T prime, that is A multiplied by S prime the only thing we still need is to multiply the both sides by the greatest common divisor. That's all. So we have proved that the greatest common divisor of every two numbers is always expressible as a linear combination thereof. This fact proves important, and we shall see various consequences of that, but nevertheless, now is the right moment to say period. Thank you, ladies and gentlemen. I hope that my little presentation was helpful. Thank you. Goodbye.